Hey, what's up? My name is Jesslyn Tannady, and I'm a developer advocate at Facebook. I'm a developer advocate at Facebook because I'm interested in empowering developer communities all over the world as we work towards inventing the future. But before I joined Facebook, I was with the MIT Human Systems Lab, working on augmented reality navigation tools for astronauts. My team worked on a NASA research project called BASALT, which stands for Biologic Analog Science Associated with Lava Terrains. And one of the things that the BASALT project explores is a combination of operations and software tools to handle the delays in communications between Earth and Mars for extravehicular science and operations. Because before we actually send people to Mars, we want to make sure that we test out all the motions here on Earth. What my work focused on was the potential of using augmented reality to aid in astronaut navigation as astronauts walk around Martian surfaces. So that's what I'm going to be talking about today, designing augmented reality navigation tools for astronauts. But first, a really brief history lesson on virtual environments. Let's start at the beginning. So in 1968, American computer scientist Ivan Sutherland published a paper outlining the very first head-mounted display that could render images as users changed their head pose. And it was really big, and a lot of what it did was render simple shapes, but he essentially created the very first virtual reality system, and it was a huge accomplishment at the time. But we've come a really long way since 1968. We've seen a lot of commercial devices that make use of 3D user interfaces. So thinking back to the Nintendo Wii in 2006, and more recently, the series of virtual reality, augmented reality, and mixed reality devices on the market. Now, people have been trying to figure out how we can use virtual environments to enhance human capabilities. And there's so many papers and apps out there that aim to figure out the potential of 3D interaction paradigms to accomplish tasks in virtual environments to make a real-world impact. For example, you see a lot of flight simulators and surgical simulators out there, and they kind of work. Like in one study of flight simulators, researchers found that participants were more engaged when trained in a specialized virtual environment simulator compared to users trained in a commercial flight simulator. So that's pretty cool. But we thought, why stop at plane simulators? Why not take this to the moon? Or like, what would happen if we tried to apply this line of thinking to future manned missions as we begin to explore planetary bodies like the moon or Mars? But here's the thing though. We want our mission durations for our future moon and Mars trips to be longer than what we did the last time we sent people to the moon on these Apollo missions. Like, in fact, lunar exploration architectures have suggested 180 days and Martian exploration architectures up to 500 days. Now, for context, the longest Apollo mission, I think, was like 3 days long. So this is like way longer. And thinking back to the Apollo missions back in the 1960s, we had people doing extravehicular activities or EVAs on the moon. And they were basically spending time outside of their vehicle, collecting rocks and doing science, and those activities were very heavily scripted and controlled by Earth mission controllers. So now that we're aiming for longer missions, the responsibility of figuring things out will have to shift towards the surface crew. And this is especially important for a Mars mission because Mars is like really far away from Earth. Astronauts could experience significant communication latencies of like 20 minutes one way, which would make it impossible for any Earth supporting crew to react quickly. Like, can you imagine an astronaut up there being like, hey, which way do I go next? And then waiting 20 minutes for that signal to get to Earth, waiting for support to come up with a plan, and then having support send that message back and waiting an additional 20 minutes while the signal gets through? Like, assuming support responded immediately, that's like 40 minutes of sitting around waiting for an answer, which is a huge waste of time and energy and, frankly, taxpayer dollars. So we try to figure out how to tackle this huge delay using operations and software. Well, one thing we want astronauts to do when they're walking around on Mars on their EVA missions is to be able to get from point A to point B effectively. We developed this tool called Sextant, which stands for Surface Exploration Traverse Analysis Navigation Tool, and it helps astronauts plan traversals on terrains that lack the infrastructure, such as roads or natural paths, because we don't have those on Mars yet, maybe. Well, what Sextant does is take in data elevation models of regions we want to perform traversals on and optimizes a plan based on metrics defined by the user. So things like distance, time, metabolic energy consumption, and it also takes into account things like obstacles and waypoints so that astronauts don't like randomly run into things. But the output of this tool is only helpful to an astronaut crew if the astronaut crew can actually follow the instructions easily. So we had to figure out a good way to communicate this guidance. Really quickly, let's break down how your brain figures out where you are in 3D space. When you think about navigation, orientation, and positioning, what you have is a feedback loop that takes in various proprioceptive cues and environmental cues to build a mental model of your space. Proprioception is to do with your perception or awareness of the position and movement of your body, and environment is, well, your surroundings. So you see things around you and you know how your body is moving through that space, and your brain uses that information to figure out what's around you. And then you rely on your senses, so things like visual feedback, vestibular feedback, and kinesthetic feedback to position yourself within this mental model of a space. So you sense things and your brain processes a ton of information every single second, and then uses that information to either support or reject where you think you are within the mental model of this 3D space. And that helps refine the accuracy of your mental model by organizing relationships between different features. Now, this process is called building a configurational schema. And although it's a natural approach to navigation, it's not necessarily the most stable because, well, human memory can be really finicky. Plus, it relies heavily on you actually noticing a bunch of environmental cues. So without sufficient cues, it can be really hard to create a useful and configurational schema, which is to say that relying solely on your memory and your senses to orient yourself does work, but is probably not the best idea for a Mars mission. Great, so let's think about what tools we can use to help us navigate. Starting with the basics, paper maps. Now, what I'm about to tell you is absolutely wild, but it's completely true. But we legit used to send astronauts to the moon with paper maps. And one time we kind of had an astronaut just wandering around up there, just a little bit lost. So what happened was on the Apollo 14 mission, astronaut Edgar Mitchell had to do a significant traverse of 1.5 kilometers, which is like a little under a mile, to the rim of a crater. But on the way, he struggled to estimate distances between nearby landmarks like craters, which made it really hard for him to get to where he was trying to go. So he basically overshot, got exhausted, and ended up extending that moonwalk by about 30 minutes, which is a really big deal when you have limited oxygen. And it's really easy in hindsight to see how this happened, because it's hard to triangulate yourself when you're on the ground and all you have to navigate is a bird's eye view map of the moon. Now, later analysis discovered that he was literally just 20 meters or 65 feet away from his original target, which is to say that it's very easy to miss when you're using paper maps in a terrain with sparse landmarks. So we decided that paper maps for Mars missions probably not the move. Well, okay, what about digital maps? Let's say like a 2D digital display on a tablet or a display on your arm. Now, it's not a bad idea. It's kind of like a GPS device or Google Maps on a smartphone strapped to your arm. And GPS devices are great because they're cost effective, they update your frame of reference as you move throughout the world, so you don't have to figure that out yourself, and you can pack additional real-time indicators like things like your ETA. And it's relatively straightforward for a user to stay on path by keeping the GPS track aligned with their current position. Now, some researchers did some studies comparing paper maps and digital maps to aid navigation and discovered that when using digital maps, users often developed a worse mental model of the space, and they're also worse at estimating how far they've walked when compared to users using paper maps. And this kind of makes sense when you think about it, and you've probably experienced this in your own life. Like when you rely too much on Google Maps, you get this fragmented and regionalized representation of an area based on strong connections between locally clustered landmarks along your route. So you might be able to recall what the houses next to your house look like, and you might be able to recall a row of shops next to each other, but it might be difficult for you to recall where these shops are relative to your house. And on top of that, digital maps still carry one of the key issues of navigating with paper maps, which is that the user needs to constantly evaluate the offset between the path and their estimated position. Like you have to keep checking where you are and where you want to go next, which means that you have to keep looking at your map, which takes attention away from your surroundings. And we really want to avoid this, especially if the interface is on a screen strapped to your arm, because when you're in a hazardous terrain like Mars, you really want to be paying attention to your surroundings, and you probably also want your arms free to, say, like block a fall. So ultimately, we want a seamless contextual computing navigation solution that lets you keep your spatial awareness and doesn't take a ton of cognitive load. Oh, and I don't know about you, but sometimes when I use Google Maps to navigate cities, I run into this situation where like, okay, I just like get out of the subway and I'm like, okay, which direction do I want to head towards? Like this, okay, there's like a CVS over there and that's where that is relative to me. But wait, am I on this corner or that corner? And it's like, wow, wouldn't it be nice if there was just like a giant arrow that would tell me like exactly where to go, like augmenting my reality? So that's kind of the gist behind this idea. We hypothesized that an augmented reality-based solution could provide key navigation information without distracting astronauts from their environment, thus allowing the astronauts' cognitive load to be dedicated to other tasks. So we went to go figure out whether this might help improve traversal efficiency, allow the user to remain focused on a real-world environment, and provide a more organic mapping of digital data to real-world environments. Now, keep in mind that the goal here is not to find a perfect end-all solution. This was more of an exploration to figure out if this was maybe a better option than the existing solutions. Now, we did this experiment in 2017. So the best thing on the market at the time on the mixed reality and augmented reality front was Microsoft HoloLens, which is what we used to prototype. And since we wanted to use holograms to communicate the output of our named the app we built HoloSextant. So while Sextant computes the optimal path between target waypoints, HoloSextant conveys the goal of allowing intuitive interaction between the user and the environment. And with that, it's time to build. Well, before we actually built the app, we wanted a way to test the app. Location not too far away from the lab so that we could actually test things. And I wanted to look for an area that had interesting terrain, because if it's too flat, then the optimal route from point A to point B is literally just a straight line. And what I wanted was a terrain that would force the navigation software to get creative with planning out a route. And unfortunately, it's kind of hard to figure that out from Google Maps. So I started looking for listicles for best places to go sledding in the greater Boston area and found this hill nearby with some trees. So we went there, flew a drone over the park, and used the drone to take photos of the terrain. And using these bird's eye view photos, we constructed a height map using a technique called photogrammetry. Now, photogrammetry is the art and science of extracting 3D information from 2D images. So in this case, 3D height data from 2D drone photos. My face from a few different angles. Using photogrammetry, you can figure out that this pixel in this photo and this pixel in this photo actually correspond to the same point in 3D space. And using that, you can create like a cloud map and reconstruct 3D models. So using these drone photos, we reconstructed a mesh of the park, and just like that, we had our height map. And we plugged this height map into the Sextant software and chose a few waypoints on the terrain, and the software planned out a path for us. So great, now we needed a way to figure out we need to figure out a way to visualize this information to the user. Now, when designing a user interface for navigation to be used on hazardous terrains, several aspects have to be kept in mind, such as like the user's cognitive load, intended interactions, and the user's surroundings. So even though the exact problem we were trying to design an augmented reality navigation tool for astronauts might have been a novel problem, what we were really trying to solve for was helping a first-person user figure out where they are in the world and where they're trying to go next. And that's actually something that video game designers have been thinking about for ages. So we drew inspiration from video games. I remember playing The Legend of Zelda Twilight Princess growing up, and there's this part where you play as Link and you turn into a wolf and you have to follow a scent. And this scent is represented as a glowing line so that you can follow the line to get to your objective. And I thought that was a pretty cool mechanic. And I was also thinking of how in Assassin's Creed, they have these waypoint objectives that tell you where you need to go. Well, at the time I was playing Brotherhood or Revelations, but basically, when you're playing as Ezio or Desmond, you figure out how to get to your objective via going waypoints and other global indicators. And I also started thinking a bit of first-person shooter games. So at the time, I was playing a lot of Overwatch. And I thought it was really cool how in first-person shooter games, you really need to rapidly communicate a ton of information to the player without distracting them. Like users need to be able to figure out where they are on a map, where they are relative to other players, how their health is doing, how much mana or ammo or whatever it is they have, on top of focusing on the actual fast-paced game. And you notice how in first-person shooter games, this kind of 2D user interface information is typically pretty subtle, but when something important does happen, like someone is shooting at you, everything flashes red to get your attention in high contrast warnings. Now, you never want everything on your screen to be super bold and bright, otherwise you'd give your user sensory overload, and if everything is bold and bright, then nothing really stands out. So we had to balance all these learnings about how to organize this visual information. We wanted to employ these techniques to balance communicating a lot of information efficiently without cluttering the visual space or confusing the user. Now, with this in mind, we outlined some of these guiding principles as we designed the user interface for this augmented reality navigation tool. First and foremost, The interface should not obstruct the user's field of view, nor distract the user from their environment, especially since the environment is dangerous and simple distractions can cause slips, falls, and injuries. So when I talk about distractions, distractions could include things like colorful objects or elements obstructing the field of view or animations. And secondly, all of the components should be easily visible, simple, and intuitive. Since the interface is aiding the user to perform a task, it must play a supplementary role. The user cannot direct full attention to the application since they will also be walking, working with team members, and performing tasks. So putting all these together, we designed and built a user interface that was made up of a 2D screen-locked user UI, kind of like a dashboard, and a 3D user interface made up of holographic elements. The 2D UI is layered close to the user and shows things like GPS status, the direction the user is facing, and the status of the path, so whether it's initialized or not. And in the 3D UI showed elements like the continuous path, waypoints, and a status indicator. We kind of went the low polygon route with the continuous path to reduce compute load on HoloLens, but also to stop the user from getting distracted by things like texture or specularity. So thinking back to our goal of reducing the cognitive load needed to navigate, we used a mix of an omnipresent overlaid path, so no recall or memorization is required, as well as several distinctive waypoints along the way. And these waypoints would allow astronauts to deviate from the path that they needed. Like, let's say there was like a really interesting rock over there, yet be able to identify the waypoints and walk back towards them and continue following the path. And we learned that when manipulating and observing objects beyond an arm's length, so like most of the path, perspective and inclusion were handles perspective view, but it's not super well suited. So for instance, at the end of this path, the part that curves around a hill, it should be hidden from the user, but HoloLens doesn't know that that hill exists because its depth sensing cameras don't have a long enough range. So the part of the path that should intuitively be occluded by the hill stays visible to the user, which is like not ideal, but the holographic path does appear to get thinner the farther away it is from HoloLens, which helps the user gauge distance. But also, we notice that the user typically does not spend a lot of time trying to gauge the route ahead because they're typically, usually more concerned about what's immediately in front of them and where they're walking next. We also implemented a status display that shows GPS coordinate values, altitude, distance traveled, time, and distance to the start or end position. And it's locked to the user view, which means that while it's not immediately in the field of view of the user, it will follow them wherever they walk so that they can easily turn their head and reference it. And we figured that with this kind of status display, it might be nice to be able to toggle its visibility on and off, because although it shows important information, it kind of takes up a... Now, if you've ever used the original HoloLens before, you know that there are a few built-in gesture interactions. So you have like a pinch, a tap, a bloom, but these interactions rely on moving your head to carefully position a tiny HoloLens cursor on a specific point in the UI and then using like a hand gesture to select. And accurately placing this cursor on a desired UI object requires very high precision, which requires time to get right, and thus a higher cognitive load on the user, which is kind of the opposite of what we want. Plus, the cursor is not always easy to locate when HoloLens is under harsh lighting conditions outdoors. So for our use case, the user must perform crucial tasks with their hands, which means that we probably want to stay away from this kind of interaction scheme. So to circumvent this, HoloSextant makes use of voice commands, which allows the user to actively provide input to the system without having to worry about turning their head or focusing on accurately positioning a tiny cursor. Now, the really neat thing about HoloLens is that it's a Microsoft product, so it runs on Windows 10, which has a Cortana voice engine. So from an implementation standpoint, it was pretty straightforward to create a custom speech recognition grammar specification. I didn't really have a good graphic for this, so here's Cortana from Halo. But as we were iterating and user testing, we discovered that naive users, so like people who have never used HoloLens before, found it difficult to recall the HoloLens hand gesture commands, but they could easily recall the HoloSextant voice commands. So even within our small sample size, it was affirming to observe that the voice commands had better recallability than the HoloLens gestures. But on top of that, we also built a 2D holographic panel into HoloSextant that displays the voice command options, so the user simply just has to like recognize the commands instead of having to recall them. We used a game engine called Unity and the open source mixed reality toolkit from Microsoft to build our app. And then we tested out our prototypes at the park where we took our drone footage, but well, the park isn't quite Mars. So what do you do when you need to test software for people to use on Mars when you don't have people on Mars yet? Well, you go to Hawaii. The Big Island of Hawaii has this volcano national park that's just miles and miles of lava terrain. So it really feels like you're on another planet, and it's perfect for running analog missions for the kind of missions we wanted to test on Mars. So think of it as a kind of like dress rehearsal comparison for what a Mars mission might look like. The Basalt team set up a mission control station, and we had people out there in the field carrying these huge backpacks as if they were carrying the weight of a spacesuit on an EVA mission. And we simulated the workflow of mission control by watching live streams of live with a delay, streams of what people in the field were seeing, and then giving instructions back. So again, all with an introduced 20-minute delay, as if the signal was really taking that long to get from mission control on Earth to the astronauts on Mars. And we also got to have a chance to test that holosextant on the field, which was such a different experience from testing it out in a park. Like in Hawaii, it was rainy, it was windy, the sun was shining really bright, so at times it was actually difficult to see some of the holograms. And on top of that, we were worried that holosextant might overheat. This sounds super hacky, but we packed a little umbrella to go on top of the HoloLens and then attached a mic to pick up the voice commands a little bit better. HoloLens as a hardware wasn't really built to be used outdoors, and we noticed that like sometimes when we looked a little bit too close to the sun, it would freak out, but otherwise it worked surprisingly well when we ran field tests. And users were able to seamlessly follow the overlaid path. And in instances where users wanted to deviate off path to check out like rock samples elsewhere, they were able to successfully return to the original path and continue their walk. We also conducted some user interviews and was pleased to hear that crew members preferred holosextant over the existing wrist displays. And I was also kind of curious to hear what the crew members thought of the app's user interface, and the feedback was surprising to me. Like some crew members liked that the path was overlaid on the ground, whereas other crew members found that they preferred a version where the path was elevated a little bit off the ground. And some users found that certain elements of the UI were helpful, whereas others found that the very same elements were actually distracting. I'm not given, the sample size of people in the field who we could survey was very limited, but my big takeaway here was that even within the user interface that we had designed, there wasn't really a one-size-fits-all solution, and that elements of the interface had to be customizable for different users. And come to think of it, a lot of video games actually already let users customize their settings, so maybe we should have made that a more central part of holosextant's capabilities. Oh, and while I was there, I met the only NASA astronaut who likes anime, and he claims that he's the only astronaut who likes anime because allegedly he outed himself as a weeb and no one said anything. So I asked for some anime recs, and if you're like me and you're into the dark fantasy genre, here's a very long list of shows that he told me to go watch. It's been like 3 years since I got this list, and I'm still working through this list. But this made me think a lot about how throughout this entire holosextant development journey, we kept drawing inspiration from video games and other bits of media. Like I could have been watching anime at 2 a.m. and been like, yeah, this is for science. And it was kind of cool to be able to incorporate things from media I had consumed for fun into this piece of NASA research. So even though I don't work on space things anymore, this experience showed me that things are just more fun when you get to bring your whole self to work. So this has been Designing Augmented Reality Navigation Tools for Astronauts. I'm Jesslyn Tannady, and you can find me on Twitter under jtannady. Thanks, and see you online.